Thank you for the excellent and precise introduction. When I got the Box medal, Antonio Pivatolo, he introduced me with 40 books, and I corrected him. It was 14. So you didn't make that. So I'm really pleased by this opportunity. I welcome comments and discussions. The topic is to introduce, so what I'm planning to do is introduce digital twins, at least the way I perceive it, and then touch on 3 topics. Then we have a list of more topics that can serve as a basis for joint research collaborations. The Center of Excellence that Pier Cesare mentioned is set up at Ben-Gurion University in collaboration with Itai Datner, Jacob Bortman, and Israel Parmet. So I looked at previous seminars and I was really impressed, and I'm very honored to join the speakers in these seminars. The last seminar last year was by Volker Merman, who gave an impressive talk on energy-based modeling, digital twins. He looked at digital twins as different models with different resolution. So this was a certain perspective on digital twins. The first seminar last year was by Irene Vignon. She talked about a hybrid modeling of the heart to manage cardiac disease in children. It's an amazing talk. I really recommend you watch it. But she talked about simulations. She didn't really mention digital twins. So as Volker said, there are different definitions of digital twins, and obviously I will give you the way I see this this opportunity for analytics. The perspective I'm going to take, this is a popular article that we had in Significance, which is the popular journal of the Royal Statistical Society and ASA. It's co-published. So the perspective I'm going to take is from an industrial perspective. This can be translated into health, into agriculture, into traffic management, and into water management. In many different areas, you will see there are opportunities, but the focus I'm going to talk about here is on industrial applications. And we are in this fourth industrial revolution, which really means that we are now looking at the factory as a data generator. So where is the data coming from? It's coming from our ability to track production, to track equipment usage, to track material, incoming material. And the way the modern factory is described is using this term of cyber manufacturing. Siemens 15 years ago talked about cyber physical systems. So now we talk about cyber manufacturing. This is a recent paper which is reviewing challenges in cyber manufacturing from the modeling and analytic perspective. This is not what I'm going to talk about now, but this is a background for what I'm going to talk about now. So if we look at Industry 4.0, where is the analytics? It's in maintenance, it's in fault detection, it's in forecasting, it's in process control. It's basically in 4 fundamental capabilities. So where is the analytics? The analytics is in monitoring. We have now capabilities for enhanced monitoring. It's in diagnostics. When monitoring raises a flag, we can figure out why this happened. So this is related to explainability and generalizability of models. We have prognostics analytic capabilities. Okay, this happened because of this. What's going to happen next? And optimization or prescriptive analytics. So the way I summarize the different types of analytic capabilities is in these four terms: monitoring, diagnostic, prognostics, and prescriptive. There are many suppliers of IT tools that are now supporting the Industry 4 ecosystem. So this is MES, PAT in the pharma industry, LIMS, data historians, and the providers of these tools, they want to sell tools. These tools combine analytics, but it's very important to keep an objective view on what are the problems. And this leads to a different perspective from the tools providers. So the elevator pitch in terms of what is going on now in Industry 4.0, if I have an opportunity to be on an elevator and I want to explain to someone up to the third floor what is Industry 4.0 about. So it's sensor technology. We can collect data on vibration, on temperature. It's cyber-physical systems, flexible manufacturing, additive manufacturing, and analytic systems that really make the sensors data and the opportunities in cyber-physical systems realized. So the four analytic capabilities of monitoring, diagnostics, prognosis, and prescriptive are helping us turn the wheels of cyber-physical systems, which are fed by sensor data. If I have 3 more floors on the elevator, I can get into a bit more details. We have physical assets. The cyber-physical systems are physical assets. These physical assets are using raw material to generate some outputs. And as I mentioned, we have sensors, IoT, that are allowing us to track these physical assets. And we have digital assets, which are digital representation of the physical assets. This is how we generate the analytic capabilities I just mentioned of monitoring, diagnostics, prognostics, and prescriptive analytics. The digital twin is different from a simulation. And here I disagree with Irene and Volker on the definition. What makes a digital twin different from a simulation is that the digital twin is fed by sensor data. So the digital asset that we're talking about has as input data that is generated in an ongoing way by sensors, IoT systems. So this is making it different from a simulation. And the outputs from the digital twin, the outputs from these 4 analytic capabilities are then used to fine-tune the system, to make decisions on the system, to improve the system. So here on the left is a robot, a real robot. On the right is a virtual twin. So this is a software realization of the robot. And we want the robot to pick up, to lift some weights. So what we have is basically a set of experiments. The robot is making some measurements, is figuring out what is the weight that it needs to be picked up. And based on this information and the model that has been used to represent the task, the robot is now executing the lift weighting exercise. So this is a simple robot. This is a simple task. What analytics does it involve? So you can think immediately that this would involve designing experiments. How do you run the experiments to make these initial weights? This involves monitoring. How do we track the performance of the robot? If there is an issue with the performance of the robot, why did this happen? What angle needs to be corrected? And we need some diagnostics. So even this simple robot gives you a hint at what are these 4 analytic capabilities that should match the robot capability. We will apply them to the digital twin, and this will affect the physical robot. This is an example from a suspension system. This is there are 8 such systems on a locomotive in a train. This is work of a student I have with Jacob Bortman. So we have the physical, the mechanistic model of this suspension system. The faults that are that are of concern are called wheel flats. This, you can see the picture of the wheel flat. The bigger the wheel flat, the more problems the suspension system will have in running in terms of the expected performance. What we are doing is, because it's a revolving wheel, we are doing an angular resampling of the data, which is a transformation of the time dimension. And on the digital twin, we can model the different levels of wheel flat, 10 millimeters, 20 millimeters, and with something called synthetic control methods, we can compare the current performance with the healthy performance and determine causal effect of the wheel flat on the vibration, which is what is modeled in the digital twin of the suspension system. Another model that is studied, developed by this student, relates to safety valves. In a locomotive, you have over 100 such valves. And this is, on the Pareto, this is the main cause of failures. 20% of failures are due to faults in brake panel valves. So this is the engineering description of the valve. And the digital twin that is using vibration is feeding some cloud data. You can see what is done on an ongoing way to track the performance of each running locomotive in terms of performance of these safety valves. This has been revolutionary. They are now tracking performance in locomotives that are running, and this has changed completely the way maintenance is done. and has greatly improved the performance of the locomotives and reduced the maintenance work actually. In revolving engines, like ball bearing engines, Bortman in his lab at Ben Gurion has developed many models to track faults. So we have a base, and the ball bearing engine is rotating. When there is a fault, you can see how the accelerometer, the vibration picked up from the sensor is picking up the faults on the outer race of the ball bearing engine. What you see here is not time, but revolution. So order means revolutions. The first revolution, second revolution. So this is the angular resampling I mentioned. And it turns out that if you run this type of analysis on time, you are getting much worse performance. So this understanding that this is using revolutions, that by analyzing data, accounting for these revolutions, you improve your ability to monitor and diagnose and make prognostics, has been quite critical. If we talk about education, and we want to give students an opportunity for hands-on experience, this is a book now in its third edition. The first edition was in 1998. We meaning myself and Shelley Zaks, we have included in this book several simulators. The book is called Modern Industrial Statistics with Applications in R, Minitab, and Jump. One of the simulators is a piston. The piston is managed by 7 factors. You have the surface of the piston, you have the weight of the piston. The simulator is using a variability in the inputs that is pulled into variability in the piston cycle time. So you see on the right the piston cycle time at a certain setup. On the bottom, you see the distribution of cycle times. And if we track cycle time, on the left, you see the panel for the jump version of the simulator. For some data, we see it's going up and down, and then it sort of stabilizes. Okay, something happened. We also figure out that the initial gas volume changed. So from a certain number, it increased. Is this why the cycle time changed? Because it's a simulator, we can run computer experiments. For example, we can apply a Latin hypercube, and this is designed by Jump. So we have a huge, this is a simulator. We can do this, it's free of charge, doesn't cost anything. These are not experiments that are physical, these are simulated experiments. With the data, we can use a neural network to model the impact of the factors. And indeed, the initial gas volume is the most important variable. So in terms of variable importance and in terms of explainability, it is what is seemingly affecting cycle time the most. We can now start doing some predictive analytics. We've seen that this initial gas volume has increased. Where is it going? We can see a huge uncertainty. What can we do to optimize? Here we apply something called a stochastic emulator. This is described in chapter 13 of that book. The idea is that the Latin hypercube or any model gives you an ability to map the average response, in this case, the cycle time response. If you run another experiment, a computer experiment on this emulator, you can also model the variability. This is what we call the stochastic emulator. So now if you combine the optimization of the emulator and the optimization of the stochastic emulator, instead of getting a solution which is optimized on the peak, you will be able to get a robust solution. In this case, if you optimize on the peak and you introduce variability in the inputs, it is a really high peak, because 42% of the time with this introduced variability, you're going to fall off the cliff. This is the failure rate that you will experience. If we optimize also on the stochastic emulator, we get a much more robust solution. It's a flat area, and by changing the setup of the piston, we are now experiencing only 1% defect rate. So with giving students the opportunity to run experiments on a piston simulator, you can teach design of experiments, you can teach process control, you can teach process optimization, you can teach computer experiments, and you can teach the application of stochastic emulators. This is an example of a vessel filling digital twin. We want to teach data-driven models, mass conservation models. So we have different topics that we want to cover in teaching students, which are in this class, which deals with digital twins. We have the height level of the water at time t, the volume V and the inflow rate U are obviously correlated. A black box approach would model this with a quadratic model. Okay, this is why it's a black box. It's an empirical data-driven model. We can apply mass conservation. Now it's a white box, which will give us how volume is changing with respect to inflow. And then we can try and match, in a specific case, the solution to this differential equation. And then we can see also some discrepancies, and some of the reasons for that might be evaporation. For evaporation, we don't have a model. So what we can do is combine a black box, which will allow us to handle the discrepancy in the model in a real experiment from the theoretical balance conservation-based model. And by doing that, we are basically running what we call a hybrid model. So it has a mechanistic element and it has an empirical element. To evaluate these models, we can conduct sensitivity analysis. We can discuss generalizability. What will happen if we change the inflow, if we change the time, if we change the scale, if we do a scale-up study. We can discuss interpretability. We can discuss causality. So basically, we have a model, and we want to assess the model. David Cox, who passed away last month, presented 4 applications, 4 interpretations of p-values, which I think is a very interesting way to open up the discussion on statistical significance and p-values. This is the reference. I won't go into the details of that, but the 4th interpretation of p-value that he mentions relates to tests of model adequacy. So he says, okay, we did fit a model. How do we evaluate it? Significant tests play an important, if largely informal, role in this aspect of statistical analysis. So this is not automated analysis. This is informal, signaling which apparently anomalous features of data are beyond those expected under the inevitably oversimplified initial model. So this is again the famous quote of George Box, all models are wrong, but some are useful. So Cox is from the Box and Cox transformation. So he also refers to that. We have taken a wider perspective beyond the traditional statistical perspective and try to discuss this wider concept of information quality. And in discussing what is information quality, you immediately have to relate to a goal. If your analysis does not have a goal, you cannot talk about the information quality of the analysis. The other elements are the data that you have, the utility function, and the analysis method. And in representing the potential of a particular data set to achieve a particular goal using a given empirical and analysis method, we have this this description of the utility of applying a method F to data X condition on the goal. These are the 4 information quality components. We did what David Hand called deconstruction. There's a paper that he wrote on statistical deconstruction. We identify 8 dimensions that really make up the information quality of a certain study. So this is beyond the p-value and statistical significance discussion. It's a wider perspective. This is the book we have, we meaning myself and Galit Shmueli on this topic. The cover of the book has already the message in the book. Some people see what's on the cover, 42. Some people don't see that. So you first have to see it. And then some people even know what 42 means. Those who have read The Hitchhiker's Guide to the Galaxy, and some people don't even know that. So yes, we talk about data, but eventually the main point should be information. And if that's the main point, we should be focused on information quality. So this is what this wider perspective consists of. In predictive analytics, we have an algorithmic perception on how to build models as opposed to the stochastics of the data generation process. So we have the training data, the validation data, and the test data. Sometimes we have just training and validation, and then we have new data. In figuring out what happens in this context, we have a recent paper called Befitting Cross-Validation, and I'll give it to you, the highlights of that. In the holdout set, we're going to take some random rows and keep them in the drawer, and we'll use those for validation. However, there are different methods available. There are other automatic methods, Venetian blinds, contiguous blocks, random subset, leave one out, jackknifing type methods. So the cross-validation story is more complex than usually considered. If we go back to the plant, to the factory plant, the data we have is structured. So we have a schedule for maintenance that affects the plant. We have data by shift or by day, by system. And if we're going to model this data with predictive analytics, we need to respect the structure in the data so that we can generalize the findings of the predictive analytics. Art Owen has a very nice paper and a YouTube talk on different structures in data. So we have rows nested in columns, columns nested in rows, balanced data, IID data, random data. I'm going to give you an example. This is a rack of drivers that are going through what is called burn-in. So the company that is producing them is trying to reduce infant mortality by running these drivers in these conditions. And the producer of these parts, of these drivers, wanted to shorten the burn-in time. So using sensor data, the question is, can we determine after 20 hours what product to release? And this is the data flow that we've used, and it includes this befitting cross-validation, which is what really made a difference. So I'm going to go over the case study. This is the general data flow for the analysis. So we have 92 units. We are able to track them up to about 100 hours. This is the way these burn-in systems have been set up initially. Some systems will break. In an event plot, you will see the systems that failed, and some systems will survive. And now we have right censoring of the data. So the blue arrows means we stopped the test and we released the product as pass. These are failed products. So the question was, using sensor data, can we reach similar conclusions here at 20 hours instead of waiting 100 hours? So here's the data. The blue go all the way, the red stop at some point. We want to figure out at 20 hours what's going on. If we don't apply BCV and we just run a regular cross-validation, so we're going to get points all over. We obviously are missing the characteristic of the data, and this is obviously a big danger. Because the data is really tracked by units, and some units pass, some units fail. And in running the cross-validation, we need to stratify the cross-validation by unit and make sure that what we are going to see is relevant to a unit and not just to a data point. We are using here penalized splines, which give us a functional data analysis perspective on this data. On these models, we can now conduct some model. We have some models, some predictive analytic models. The analysis now is using the model that we got from this penalized spline on the trajectory of the drivers. And we have several sensors. Here you can see that we use the functional principal component, the first two of a key parameter called key parameter 1. We actually had more than one key parameter. We have the condition of the driver, passed or fail. This is from the data. We have the cross-validation that is accounting for the structure in the data. So the validation column is splitting the data into training and validation set. On the training, we apply a neural network to predict the outcome of the driver under test. This is a decision tree perspective, or regression tree actually. And what we end up with in the validation set is almost perfect performance, so that applying befitting cross-validation to this analytic model, we can show the customer that at 20 hours, we give them a rule to decide on whether to stop or continue the burn-in, which obviously they were happy because it saves them 80 hours of testing. So I'm reaching the end. I was told 45 minutes. Some research topics. This is just a list that we compiled. In this area of digital twins, we can talk about adaptive and online learning of statistical properties. We can talk about the mathematical properties of uncertainties in the model and in the equations and the parameters of these dynamical systems. We can focus on quantifying the uncertainty. We can find ways to optimally integrate mechanistic and non-parametric data-driven models. We can focus on optimal design experiments in the development of digital twins, so that we have optimal monitoring, diagnostic, prognostic, and prescriptive analytic capabilities. And the propagation of statistical error is something that is obviously affecting digital twins, and this is another area that might be worth further looking into. So this center of excellence we are setting up is designed to provide a platform for this. We have in mind both research, industrial applications, and education. Education means we have students who are going to do graduate studies in that center. There are already 3 students. We also plan on running workshops through different forums, so that proper analytics in the context of digital twins is better known. So this is a summary. There is a gap. I'm sure you have all experienced that, between academia and industry and startups. So the 3-legged stool has startups, academia, and industry. And I think MOX and what you are doing is exactly on this interface. This center we are creating is also aiming at filling this gap between these 3 considerations. I gave a brief intro to Industry 4.0. I talked about empirical models and mechanistic models and hybrid models that combine them. I talked about validation with befitting cross-validation. So the general talk was on digital twins and data science. So Pier Cesare, I think, has a nice way to describe data science. It's data and science. This is why I asked you the question last time.
I know. I was ready to ask you the same question now to see what is your answer to this problem, but you spoiled it. Okay.
Yeah, we can discuss that. And through this platform called Digital Twin, we I think have a nice trick, quote unquote, to push forward analytic capabilities in terms of monitoring, diagnostics, prognostics, and prescriptive analytics. Besides the mathematical, statistical aspects, there are also organizational aspects. This is a short book, which is titled The Real Work of Data Science. It talks about everything but mathematics and statistics. And it basically discusses how data science can be deployed in organizations. 18 chapters, 3-4 pages each. It also has an Italian version, so you have the Italian version on the left. The book was recommended by David Cox that I mentioned before. Here are some other books. I mentioned the information quality book, the modern industrial statistics book. There is an edited book we have on systems engineering in the fourth industrial revolution with, I think, 4 or 5 Italian authors. A lot is going on in Italy, and we are very glad for collaboration opportunities. I also had another book on systems and software testing. Testing and validation is obviously a data generation process, and there are lots of opportunities in that playground. So I'm 5 minutes late.
Wow, thank you, Ron. This is very inspiring talk, I would say, and also your very open talk, because you mentioned many problems, but in a very general context about digital twins. So I'll now open the floor to questions and comments, and I don't know how it works. If there is maybe Christian can help me here. I don't know if there is okay.
Yes, we can ask to the audience if are there any
Do
questions.
they raise their hand here in Zoom? I'm totally confused about the different platforms that we use every day. So do they have the hand raising here or not? I don't remember.
Let's see.
Otherwise, I can start with a sort of a breaking ice. Okay, you're not allowed to ask a question to yourself, Ron. So anyway, at the very beginning of your talk, you mentioned a difference between simulation, let's say, so modeling, either data-driven modeling or physics-based modeling, and then building up a model for doing simulation, and also to try and test what we have modeled under different scenarios, and digital twins. And you said, I do not agree with the fact that the two terms are somewhat exchangeable. I think that there is a basic difference based on how they use the information coming from sensors. Now, I'm totally naive about the digital twins. I'm not an expert at all, so I can, but I know you, and so I can sort of ask the question, even if it's a stupid question. So can you elaborate a little bit more about this? Because at MOX, we, of course, are in the business of building up a lot of mathematical modeling for phenomena, either social phenomena or real phenomena, or physical phenomena, and so on. And I think we are also used to what you called hybrid models or physics-based model, where you try then to capture maybe left any information in the residual of the model and so on. But what is this basic difference between simulation, general term, and digital twins?
So, I start from the end. I'm looking for enhanced monitoring. So enhanced monitoring means you are tracking an operational system. To track an operational system, you need ongoing inputs. if your simulation does not involve ongoing inputs, it cannot provide monitoring.
Okay.
So my litmus test, it's very simple. I get it in 2 seconds. Do you have inputs, ongoing inputs? Irene did not have ongoing inputs. So what she's talking about is not a digital twin.
Okay. So if you have a data stream that enters into the simulation and
yes, and this is posing Alfio, I'm sure, will able to also continue on this. This is posing very interesting challenges because you also need what we call chronology of data and goal. If you are not able to provide the feedback in a timely way, it's not monitoring, it's not good monitoring. So this opens up, this is not something that people in statistics are usually concerned about.
Sure.
So if you think about this combination, I think it also poses interesting research questions that you are not, Michael Jackson from Berkeley, yeah, not the other one.
Not the player, not the basketball
player. The first one, yeah. This is what he's pushing. You know, we need to have a balanced view. When you're taking an algorithmic view, it is also about response time. Response time has never been a consideration in statistical properties of models.
Okay.
In the paper we have on this review of cyber manufacturing systems, there is another thing that is mind-boggling: the data flow. Your conclusions are dependent on the data flow. This is another thing that is not taken into account in statistics.
Yeah.
People who've done studies on analyzing fMRI data, the same data, the same questions, 80 teams, 80 teams, on more than half of the questions, they get different answers. Why? Because they use different data flows. The data preparation, the data integration, it's done differently. So the conclusions are different. We need to be aware of this, and we need to find a way to address this.
Sure, sure. I see that Alfio has a question.
Well, first of all, let me say that, thanks a lot for your talk. I really enjoyed it. And I love your vision at the end with the fault in between the three, you see, the three entities, which is academia, industry, and startups. And I have to say that I fully agree on this vision. And this is a reality indeed. And I guess you pointed out very, very precisely what we need to fill those gaps. Now, back to the issue of simulation versus, say, simulation and digital twin in a very, very constructive manner. First of all, I'm very intimidated because I'm not a digital twin expert, right? I try to understand, and I try to see if what kind of role we might have. And in my very simplistic, hyper-reduced understanding, things are very clear to me, and maybe are clear because I'm wrong, right? When you oversimplify, maybe you can get wrong. So here is the physical twin, whatever it is, right? It is a machine, it is the society, it is a human being, and here is the digital twin, right? It's digital twin.
Yes.
Okay. The way I understand it is that this guy, the physical twin, through sensor, through wearable devices, through measurements, provides continuous data flow to the digital twin, right?
Yeah.
And this digital twin should have the possibility to elaborate in quote, 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 real time, right?
Yes.
This information and return the feedback
Yes.
to the physical twin,
right?
And controlling it or managing it or whatever, driving it, right? Improving, optimizing use all these verbs that are useful in the specific situation.
Yes.
Now, there are two basic requirements. One is real time. And I agree with you. You need input data. So forget about now the talk by Irene that I even forgot. I mean, I caught some of the aspects of her talk, those more related to computational medicine, but frankly speaking, don't remember the relationship with the digital twin, if any. Forget that, right? Of course, here on the digital twin, you need input of data. And here you may have parametric or non-parametric models. You may have physics-based model or data-driven model. It does not matter. You need models that are suitable to provide a feedback to your
Yes.
physical twin, right? Now, if you have non-parametric, say physics-based models / simulation, the important thing is that this guy here should be able to describe the relevant aspect you want to control or to manage from the other side in due time. Before you have been presented this vessel filling digital twin model, and we're using conservation law, right? In the form of a partial differential equation. So I'm not dogmatic here. I may have any model that are suitable to describe what you need from the other side. And if this model is a differential model or a model based on numerical simulation, fine. If a purely statistical model, data-driven model, fine as well. What is important to me is that the model be adequate to provide the answer that are needed
Yes.
for the physical twin, right? That's my little understanding.
Yeah. Alfio, I don't think we have any disagreement. Simulations are part of the digital twin. It's not
Okay.
like I'm saying, okay, the only thing I think terminology is important, because otherwise things become very confused. I was involved in there were discussions on reproducibility, replicability, and repeatability, and it was cacophonic. People use these terms as a matter of speech, but they actually have definitions. And if someone says reproducibility, replicability in the same sentence, it's cacophonic. So I'm trying now to establish the distinction between digital twins and simulations.
Sure.
And this terminology is because people can use terms. There's no law against the term. So that I'm trying to put this in perspective. Just to emphasize, so in my chart, the inputs back was a green. There was a green arrow to show the inputs back. But just to emphasize something that came up from your comments, we have sensors and we have soft sensors. Soft is not soft. Soft are software sensors. So some of the data we can get from computation, not from technology, which means if we have sensors that have issues, maybe there's missing data, or maybe there are problems. Now, maybe we can combine models in the data that is received. We can definitely combine data that is needed online with data that is coming from the laboratory 3 days later. The most striking example is what you have at the gas station. You fill in your car with 95. This is called RON, R-O-N.
Okay.
It takes 1 week to measure it. So if you are a refinery, a petrol refinery, and you have to wait 1 week to know what you have, it's making life very difficult. So they have a soft sensor that estimates RON online. And then they calibrate it and they do all sorts of things. So there is a whole opportunity, you can imagine, of combining measured data with estimated data to run these models that can be simulations or physical models, etc. So then there's another dimension of unstructured data, images, sound, text. We can combine all of this. We know how to do it. This is 2022. This is amazing. 2022. 10 years from now, nobody thought about that. This was considered only, only NASA and, supercomputers. Now you can do it. You can do it on your iPhone.
There is another question. Thank you, Ron. There is another question from Andrea Matta. Please, Andrea.
Yes, hello. Thank you for your nice talk. I'm not a mathematician. I'm from mechanical engineering, and my group is working on digital twin of production systems in plants. Okay, so I agree with you with your vision. A digital twin is something that is getting real data and is providing a feedback. And it can do it with a model. It can be a simple model, like for instance, I can collect the data, I calculate a sample average, and this can be my prediction model for the next day.
Yes.
Or I can do with a complex simulation model, but anyway, we'll use models. Very likely that in the future, a digital twin will use several models depending on the decision, depending on what the digital twin is used. I would like to ask only two things. Okay, your opinion on two issues that generally we have in production systems. So a production system or a production plant is not stationary. The life
Yes.
has at least 20 years, and after the first week is changing.
Yes.
The production rules are changing, the operators are changing. I add machines, robots, and so it is changing. The digital twin might be very expensive. So the first question is how to adapt the digital twin to follow the system change, because if
Yes.
the company cannot afford, programmers always following the real change. So how to automatically adapt a digital twin? The second question is about synchronization. Now you are assuming that the data flow is continuous and
Yes.
cheap. Okay. What about if the data flow is expensive, or your simulation, the effort to simulate is expensive, so it takes time, so you cannot synchronize continuously, so you have to make a decision how to manage this. And then I would have other questions, but I stop here.
So I like to start with the application. So if you go to companies, they have operations and they have maintenance. The maintenance group is in charge of running maintenance schedules. The operations group is in charge of running operations. You want to help them introduce condition-based maintenance, not with a fixed schedule. So now you need to have data from operations and you need the data from maintenance integrated, fused. This is a first step, which is an eye-opener, because in many companies, the data of maintenance is in one database and the data of operations is in another database. So now you're going to do this data integration. They are not synchronized. They are not synchronized. Maintenance is running a certain life cycle and operation is running a different life cycle. So you need methods to make this relevant. Part of it has to do with the data representation. The example I gave on the burn-in of drivers is doing some of this because because you have the characteristics of the driver, you have the sensors on the drivers, and you have what happens during burn-in, and all these are working on different clocks. So one of the things that you need to figure out is how to do this data integration. And the other thing is how to model changes, which was your original question. There are analytic methods that can allow you to do so. Wavelets, S-flex, there are methods that are adaptable. So there are analytic methods that will allow you for this adaptation in terms of the analytics. If you have physical models, so you have a physical understanding of what goes on, then obviously you know how to do the adaptation because you understand the physics. So you know what happens if the temperature goes up, you know what is going to be the impact on the process. So your questions are very good. I don't have a simple answer, but I like a lot the talks of Judea Pearl on causality and physical models. He mentions that if you have an equation in physics, it doesn't imply causality because anything you change in the equation will affect the other things, but this is not what is going on. Real life has some causality. There's one thing that will affect. So he's pushing for graphical models, the DAG models, the direct cyclic graph models. These, I think, will allow you to do what is called transportability or generalizability of analysis. So let's say you train the model in situation A, the situation changed to B, you can adapt it. There are methods to adapt it. Now, regarding the definition of multiple digital twins, to me, I think this is a matter of aesthetics. I say there is a digital twin, one digital twin, maybe different resolution levels. Because if you break it into multiple digital twins, I think you missed the point. This was the talk, the talk before me. I like it as one with different resolution, and then the question becomes, what is the right resolution for the application that you are doing? And that is valid. I think to match the resolution with the proper model, I think is a valid question. Yeah. It is not a different digital twin for me. It's the same.
I was meaning multiple models.
Multiple models, fine, yes. But we need to be clear and simple in what we are in the message. What people say now, there will be digital twins everywhere now. Any system, any production, any service, people say that companies move from products to services. Rolls-Royce is renting time on their engines. They're not selling engines. You are paying by the hour. So if you are becoming a service provider, the importance of digital twins grows immensely because now you are in charge of managing the system. So it's not like you sell it and you forget it. So I think it's very important to lay properly the foundations for robust developments in digital twins. And the applications are everywhere. In agriculture, I heard the talk on digital twins of wineries, growing wine, the wineries. So how do you treat the plants? And they have sensors in the soil, so they can tell you exactly what's going on 24 hours a day. If they want to optimize, they can set up a digital twin of the plants, and they will have predictions. It will improve the supply chain. The challenge is, of course, how do you also educate students in this? That's another topic, because it requires, I think, a multidisciplinary perspective. To teach this is bringing in different topics, and the students now they like one topic at a time. When you start integrating topics, they get lost. You know, they don't understand what you want. So people talk about multidisciplinarity. It's a opportunity for pushing forward multidisciplinarity. The topic of digital twins.
Very good. Ron, there is a question that has been asked through the messages from Filippo Notarnicola. What is the relationship between digital twins and data assimilation? So it's another terminological question, let's say. What is the data assimilation and digital twins?
So data assimilation, I know about data integration, data fusion.
Yeah, that could be too technical. Maybe Filippo,
Please,
are you with
yes,
us?
I'll be glad to learn about data assimilation.
I think, well, people working in numerical analysis talk about data assimilation. Maybe somebody who can share this knowledge with Ron.
So maybe I can try to give my own perspectives.
Exactly.
Data assimilation.
I don't know. Maybe Filippo is with us.
Oh, Filippo, of course.
Of course.
Filippo.
But Alfio, give you your perspective to us.
Well, data assimilation is when you have, sorry, basically you're running a model that needs data. And well, a typical example is when you make predictions with for the weather, so weather forecast. So you start your model that makes simulation for the next couple of days or week, say. Yes. And meanwhile, while your model is computing, meanwhile you have new data coming from satellites or from any source of data. And you want to integrate your data or assimilate your data, which are no longer data, they are solutions, part of the solution, yes, into your model in order to improve the model itself. And this is very often the case when you have lack of data. For instance, in medical application, you are working on a real patient and you need many data on that patient concerning the viscosity for his blood rather than the elastic properties of his myocardium and so on and so forth. You don't have all those data, so you have only partial data. But then you have measurements that come from the clinics, and you want to inject or assimilate those measurements, which are part of the solution, to improve your knowledge of data, say, yes, assimilate data. Here I see the situation a bit different, because here I'm really, figurating the two players, right? The physical and the digital, which have to exchange data and solutions, but not in the, say, in the spirit of the assimilation. Simulation is similar from the mathematical perspective, but I believe that the application here is very different. That's my personal understanding.
So, yeah, thank you. I will look at, the last time I took a course in numerical analysis was many years ago. So this is interesting. There is something called knowledge transfer methods, where some conceptual conclusions from A are used in B. And so I know of papers on knowledge transfer methods. But I've never, I don't know about the assimilation aspect, and I will look into it. This is very interesting. Could be very relevant, but I don't know, basically.
Very good. So I think I think we can stop here and thank Ron again.